In our previous video, we looked at how electronegativity created a unique reactivity for water. Right? So we had our highly electronegative oxygen pulling electrons in these covalent bonds towards our oxygen. So we end up with our oxygen becoming slightly negative because those electrons are more towards our oxygen than they are towards our hydrogens, and our hydrogens become partially positive. This results in this area of high electron density around our oxygens, right, because they're pulling those electrons in towards that oxygen, and areas of low electron density around our hydrogens. So these have low electron density, and we have high electron density up here on our oxygen. Again, of course, we then use specific terms to refer to these areas of lower electron density and higher electron density. So we refer to an area of low electron density as an electrophile. So this just says that it would love to get more electrons because it doesn't have a lot of electrons. Right? It has a positive charge, so negatively charged electrons are going to be attracted towards those hydrogens. On the other hand, our oxygen now has that partial negative charge because it pulled those electrons more towards itself, and so we have this area of high electron density, and we refer to this as a nucleophile because it can use the extra electron density and it wants to seek out other nucleophiles that will have more positive charge. Right, so it's going to be attracted towards positive charges. So what we see with our water is that we have an area of high electron density, that nucleophile, and an area of low electron density, our electrophile. And this is going to determine the reactions that our water will have. Now in general chemistry, one of the key reactions that we looked at with water was the reaction of an acid added to water, or the reaction of a base added to water. So we could add something like HCl, or hydrochloric acid. As the name suggests, this is an acid, and of course our definition of acid is that an acid is something that will donate an H+, a hydrogen plus ion. So following our normal general chemistry, we'd say, okay, we have HCl. As our acid, it's going to donate H+, so we take away the hydrogen and add a positive charge. That's going to react and give us our H3O+, right, because we add the H+ onto our water, our H2O. And then our chlorine will remain behind. We took away our hydrogen, we also took away a positive charge, so this becomes our chloride anion. So our products here are H3O+ and Cl-. We would refer to this as our conjugate base. And this would be our conjugate acid that are produced from our acid-base reaction. So this sort of reaction equation is what we would typically show in general chemistry. Right? So we would know, just based off of our key definition of an acid, that it's donating that H+ ion, and then we can use that to predict what products will form. Now we want to go a step further here in organic chemistry, and we want to actually show why this reaction is occurring and how our electrons are moving in order to make this reaction happen. So let's take a closer look here. So first with our hydrochloric acid, so we want to add in our extra electrons. So remember, chlorine is on the far right hand side of the periodic table in group 7A. So that means that it has 7 valence electrons. We have 6 that are non-bonded electrons in these lone pairs, and then 1 electron is shared here in our covalent bond with hydrogen. So that gives us our 8 electrons and a full octet for our chlorine. Our hydrogen here has those 2 electrons which fill up its outer electron shell and give it a full octet, we would say, as well. Now, as we saw before with water, the next thing we have to do is show if there's any electronegativity here that's going to change the distribution of electrons in our molecule. So chlorine is on the far right-hand side of the periodic table. That makes it relatively electronegative, so it's going to be pulling the electrons in our covalent bond towards itself. And we again have an area of higher electron density on the chlorine, or a nucleophile, and an area of lower electron density on our hydrogen, our electrophile. So, our electrons are already kind of pulled in this direction, away from our hydrogen. Now, what's going to happen when we add our water together with our hydrochloric acid? So our water has this area of high electron density, right? So that's our nucleophile. And it sees this area of low electron density. So if we take some of our electrons and share them, right, so that negative charge getting attracted to the positive charge, we can create a new covalent bond. And as we know from our overall reaction, that's what we need to happen. We need to make a new covalent bond between a hydrogen and an oxygen in order to form our product. We're going to represent this using what we call a curved arrow. So I'm going to show an arrow that's going to show the movement of electrons. So I show that arrow showing my electrons here from my non-bonded lone pair moving over to my hydrogen. And it's these negatively charged electrons are attracted to that partially positive charge electrophilic hydrogen here. So this is my curved arrow again. My curved arrow is always going to represent 2 electrons moving. So that shows my 2 moving electrons moving over from my oxygen to my hydrogen as I'm forming a new covalent bond there. So my electrons are attracted to that positive charge. Now hydrogens, of course, can only form one bond, right? So we'd form one bond between our hydrogen and our oxygen, but we already have a bond here between our hydrogen and our chlorine. Now our chlorine, of course, it's already pulling these electrons toward itself. So what we can do is we can just take these electrons from this bond and move them over onto our chlorine. And what this represents is our bond is breaking, those 2 electrons are moving over, and they're just going onto our chlorine. So each of these arrows are representing 2 electrons moving. We have our lone pair of electrons coming in, going to our hydrogen and creating a new bond between our oxygen and our hydrogen. So we're going to end up with this structure here, as our lone pair formed a new covalent bond to that hydrogen. And of course we still have 1 lone pair remaining on that oxygen. These 2 electrons from our bond are moving over onto our chlorine. And so we end up with 4 electron lone pairs on our chlorine. So these are our overall structures here. Now, of course, we also have charges here for our products. So we know that this is going to be positively charged and this is going to be negatively charged. We can also be a bit more specific, and we can show where these charges are at. Right? So our chlorine gained electrons, and so our chlorine, we'd say, is negatively charged to create this chloride anion. So it has more electrons around it than the number of protons. Right? So with that extra electron that we now have 8 valence electrons instead of our normal 7 to give us a negative charge overall. Now for our H3O plus molecule here, our hydronium ion, we know that we're positively charged because we lost electrons as we formed as we gave them away to our chlorine atom, but we don't know where that positive charge is focused. Now, in order to determine where our positive charge is focused, we want to look at how many electrons each of our atoms would expect to have normally, and then compare that to how many electrons they have now in our current structure. So we call this our formal charge. So a formal way to calculate this formal charge would be using our equation where we say that the formal charge is equal to the number of valence electrons minus the number of electrons in lone pairs and minus half of the bonded electrons. So when we want to calculate this formal charge, we're essentially saying that our electrons in those covalent bonds are split evenly, even though of course we know they're not split exactly evenly. So we give one of the electrons in each of our bonds to each of our atoms, and then we count up, of course, the lone pair electrons that are just associated with that atom there. And we subtract these from our valence electrons to look at how many electrons we actually have in our molecule. So these are kind of our actual valence electrons. Versus how many our atom would like to have. So we normally expect to have 6. We actually have only a relative share of 5. And so when we subtract 5 from 6, we get +1, indicating that our oxygen has less electrons than we would normally expect to have. We still, of course, will have these electrons pulled towards our oxygen. So our oxygen is still electronegative. It's just that because it used its electrons to make this new bond, it now actually is somewhat electron deficient. It has that positive charge since we took these extra electrons and bonded them to our hydrogen. So again, we use those electrons to make a bond with somebody that was electron deficient, our hydrogen. Our chlorine, it wanted those electrons because it's relatively electronegative, so it pulled those electrons toward itself and became our chloride anion here. So note with our chloride anion, of course, we have all these 8 electrons to make our octet fulfilled here. So we just have our single anion here that is happy all by itself with that full octet of electrons. Okay, now let's compare our previous reaction of an acid reacting with water with the reaction of a base reacting with water. So here's our base. This is ammonia. Ammonia is a common base. It's contained in a lot of different household cleaners. Bases, again, our basic definition of base is something that accepts H+. Right, so it's going to take H+ from another atom, another molecule, an acid, that's donating that H+. So in this case, our ammonia here, so it takes the H+, it becomes our ammonium and H4+, our water donates the H+, and becomes our OH- hydroxide ion. So again, let's look at this using our arrows to show electron movement and the overall reactivity of our compounds. So our nitrogen is electronegative. It's pulling electron density towards itself. We've got the same thing over here in our water. The oxygen is electronegative and is pulling electron density towards itself. Again, this creates our reactive sites, areas of high electron density and areas of low electron density. Now our nitrogen is going to be taking an H+, since it's reacting as a base. So we have this area of high electron density, and we want to take our electrons here. We have extra electrons, so we're going to bring them over, bring those negatively charged electrons towards our positively charged low electron density hydrogen. Again, it's a partial positive charge, not a full positive charge, but we can still look at it as a negative charge coming towards something that's more positively charged. Again, at the same time, we can't have two bonds to our hydrogen because then it would have more electrons than it needs to fill that outer electron shell. So we also take the electrons from this bond and move them over towards the electronegative oxygen, which is already pulling on those electrons. So it's just pulling a little bit harder to break the bond and bring those electrons over to our oxygen. Again, we show those electrons moving with our arrow. The electrons are going from this bond, the bond is breaking, and we're dumping those extra electrons on our oxygen to make a new lone pair. So this arrow makes our lone pair. And this arrow makes the new bond. And of course it's using those electrons from that lone pair to make that bond. And again, that's what we see over here. We see a new bond to a hydrogen that formed from our arrow, and we see a new lone pair formed from our bond breaking and our electrons moving over to our oxygen. So again, we can explain what's happening overall based on our sites of reactivity. We're taking electrons from a high electron density area, putting them in a low electron density area, and then we can also show what's happening using our arrows. New bond forming, using those lone pairs, bond breaking, and new lone pair forming, using those electrons from our bond. Again, we can also use our formal charges, and we can look at the relative distribution of electrons in our products as well. So if we look at our oxygen, we have 6 valence electrons that we expect normally, and in oxygen we subtract the number of electrons in lone pairs, so we have 6 now in lone pairs, and then we subtract half of the bonded electrons, because we're assuming that these are equally shared, one on our hydrogen, one on our oxygen. So that's half of 2, or 1, and this becomes a formal charge of -1. So our oxygen has excess electrons, and the negative charge is focused on our oxygen. Our oxygen is very electron rich. As we go over here in our ammonium ion, so our nitrogen here normally would expect to have 5 electrons, right? So nitrogen, it normally has 5 valence electrons. It's in group 5A. So here in ammonia we can see it has those 2 in the lone pair, and then it would have 1 each in these bonds that it's sharing with our hydrogens, 1 from the nitrogen, 1 from the hydrogen. So we take those 5 valence electrons that we would expect to have. We don't have any lone pairs here, so our nitrogen doesn't have any electrons from those. We have 4 bonds with 2 electrons each, so that's 8 bonded electrons. We assume that we get half, roughly, of the share of those bonded electrons, and this gives us +1 overall. So our nitrogen actually is the one that has the brunt of that low electron density, that positive charge, because again, it used its electrons in order to make that new bond with our hydrogen. So we get this +1 formal charge. An easy way to look at this, so normally oxygen with its 6 valence electrons would have 2 lone pairs, right? So we have our 2 lone pairs and our 2 single electrons. Anytime we gain a lone pair, we gain a negative charge. over here with our nitrogen, so nitrogen we'd normally expect to have 5 valence electrons with 1 lone pair. As you can see here in our structure, we have 0 lone pairs, so we have 1 less lone pair than we expect. Whenever we have less lone pairs than we expect, that means that we should expect to see a positive formal charge on that atom. So we have 1 less lone pair, and we end up with this positive formal charge. For our initial water and ammonia, of course here we have as many lone pairs as we would expect. So these have no formal charge. They have a formal charge of 0. We can also calculate that formally using our equation. So it would be 6 is the number of electrons we expect for oxygen, minus 4 electrons in our lone pairs, and then minus half of those electrons in our bonds. Half of 4 is 2. This comes out to 0 as the formal charge for our oxygen. We can do the same thing over here for our nitrogen as well. We take the 5 electrons that we'd expect, subtract the 2, subtract half of those 6 electrons that are shared in our bonds, and we again get a formal charge of 0. Again, the formal charge just kind of shows us if our specific atom has more or less electrons than we would normally expect it to have based on the usual number of valence electrons for that particular atom. What we see overall here again is that regardless of what our formal charge is, the electron density based on our electronegativity and where we're pulling our electrons can kind of show us how our electrons will move, which again we can represent with our curved arrows in order to make our particular products. And again, this will be key for our other organic reactions as well. So we can expand our idea of reactivity based on electronegativity to predict different organic reactions, and we'll use our curved arrows to show how those reactions are occurring, how our electrons are moving through our molecules to create our new products here.